right, thank you for coming along to today's Earth Science seminar. So we've got two speakers ahead. We've got Darwin and Derek, who will both be giving talks today. So first off, we'll just do a quick acknowledgement. We acknowledge and pay our respects to the Kaurna people, the traditional custodians whose ancestral lands we gather on. We acknowledge the deep feelings of attachment and relationship of the Kaurna people to country, and we respect and value their past, present, and ongoing connection to the land and cultural beliefs. So Derek obtained a PhD in geophysics at the University of Utah in 2010, working on the thermal state of the oceanic and continental lithosphere. He then worked for 3 years as a Green's Scholar at the Institute for Geophysics and Planetary Physics at Scripps Institution of Oceanography, where he built a high-temperature electrical conductivity apparatus for studying mantle samples. Now at the University of Adelaide, Derek has focused his interests to the distribution and physical and chemical processes that control radioactive heat generation in the crust.
All right, well, thanks, Darwin. That was great. And in some ways, that's a good introduction to what we want to sort of achieve with some of this, is actually sort of improving on some of those things that you can do with laser maps. And I will say right now that this doesn't have to be just done with laser maps. It's possible that we can write this software so it can do anything with XY type data. So it doesn't have to be a laser map. It could be even, I don't know, magnetic data. You could almost put into some software like this if we get to that point. Anyway, so what we're looking at is a software for looking at LA-ICP-MS laser maps at the moment with multi-element sort of analyses. It got started, I got interested in this when one of Martin Hand's honor students last year walked in my office and said, hey, I've got these really interesting images of pyrites. And we know that they have sort of these interesting ratios of nickel and cobalt, but there's a bunch of stuff in these maps that aren't pyrite, and we want to be able to separate the data of this pyrite from the data that's not. Is there an easy way to do that? And so I sort of said, yeah, we can have a look at that. And I just happened to be walking past Simon Carter's office, who was visiting Graham Heinzen at the time, and was playing with fuzzy clustering, and I'd never heard of that. And I said, hey, can you explain how that works to me? And after he told me how it works, I was like, oh, I've got the perfect thing to use that on right now. So anyway, so here's an image of sort of an early version of the software. Well, I should say, this is work that we're doing for the MinX. Martin Hand, Stan Glory, and Alex Van Leeuwen are all part of the project with me. And Siobhan, who's up back there in the background, is our sort of genius coder, who's sort of putting together the working version of the software as opposed to my buggy version. And I've been playing with data from all of these other students here. So normally you go and you collect a bunch of LA-ICP-MS maps, you get something that looks like this, and then you got to make sense of it. So now you've got a bunch of maps, and the first thing you do is probably some sort of qualitative analysis. The first thing you might do is sort of say, okay, well, let's sort these maps into some sort of way that makes sense. So I've just sort of taken these maps and grouped them based on different features that I can see in the data. So the top one, you're looking at a garnet, which you can tell by the aluminum, the calcium that's predominant in the sample. And you can see all of those maps in the top really sort of focus on the garnet. That's sort of the big feature that you can see in the data. The next one down there, you can see sort of rims and cores of that garnet, very nicely expressed in the heavy rare earth elements. And then on the mid to heavies, and then some of these other elements you're sensing other accessory minerals that are also in there. And even in lead and lithium here, you might be actually seeing fractures that are in the garnet that you can't actually see with the other elements, or at least not as clearly. And then with some of these other elements, maybe we're seeing inclusions or something like that. So there's a number of different features that we can see in these maps, but what we want to be able to do is sort of look at this not in a qualitative way, but start to do this in a much more quantitative way. So we've been developing this Laser Map Explorer. I'm going to call it LAME as an acronym for start. This is version 0.0. So this is the buggy version that I've created. It works depending on the day, because I sort of work on stuff and then somebody says, hey, can you add this to it? And I'll add that and then it breaks. So it is actually very lame as a software at the moment. But those are some of the things that we'll get into more of that in a bit. But one of the things that we really want to do is try and tease as much information out of it as we can using sort of multidimensional analyses without having to look at every single map and try and do something individually with every single map. You can still do that with this software, but the point is that maybe you have a bunch of samples that you've collected and you don't want to have to go through 10,000 maps to try and get something reasonable out of them. The idea is that this way you can process the data much more quickly. You can sort of set up a processing stream with one sample and then run it through all of them. Machine learning can be grouped into two types, supervised and unsupervised learning, okay? So supervised learning, some of these are a bit of a misnomer anyway, because it doesn't matter what you're doing, you still have to look at the results and try and determine whether they're good or not. So you still kind of have to supervise what's going on. But the main difference between supervised and unsupervised learning is whether or not you know a class to different objects to start with, okay? If you don't know what those classes are, you're doing unsupervised learning. If you know what those classes are, you're doing supervised learning. And by classes, I mean maybe labels of the data set, okay? So supervised learning, one of its drawbacks is it can be slow to train. It requires expertise. You have to kind of know what you're doing. If you put in sort of the wrong training data set, then you can screw everything up and get a bogus result that doesn't mean anything. So you kind of have to know what you're doing. But they can work very well and are very accurate if you actually get good at understanding how to do this and do it properly. You can actually get really, really good results. Anyway, the supervised learning though falls into a couple different types. One is classification, where you're trying to say which bin does this fall into, and the other is regression. So if you've ever done linear regression, in some ways you've done a supervised learning because you've got group A and group B and you're trying to find a relationship between them. Unsupervised learning though, like I said, you don't know what those labels are. You're trying to sort of group them so you can ascribe labels to them. It's much faster to train than supervised learning techniques, but it can at times be a bit more difficult to interpret, though what I'm going to show you is with the maps that we'll make, they're actually not too bad for these mineral maps, probably because minerals have sufficiently different chemistry that they're easier to understand. And as Martin would say, you never put anything under a laser that you don't already know what it is. So you ought to have a pretty good idea of what these are anyway. Okay, and this type of clustering falls into three different types. We're really only going to focus on the clustering, and I'll show you an example of k-means, but we'll actually be doing fuzzy clustering. So there's only subtle difference between them, and I'll get to that later too. Another type too that we also do is a dimensionality reduction, principal component analysis, which is sort of a useful technique for reducing those sort of 20 or 30 maps that you've collected and saying, how many maps might I actually need to actually understand this? And by combining them in a certain way, you can reduce the number of maps that you actually need to look at. So I'll show you how that works as well. Okay, so let's think about supervised learning. So I love Mexican food. One of the things we make every time we eat Mexican food is pico de gallo. That's sort of where you start when you're making salsa. So it requires a few ingredients here, requires limes. So let's say down here in my class labels, it requires limes, tomatoes, jalapenos, and onions, okay? So those are my classes. I've got this training data set here. I'm gonna stick it into a blender, turn it into a bit of a mush. Comes out here. I can then take my trained classifier and try and say, what is in this? Can I tell what's in this? And then based on a training data set that's been through the same process, I can taste that and say, okay, I have tomatoes, jalapenos, onions, and limes, okay? So that's the way supervised learning basically works. So you have to come up with a training data set and a testing data set that you use to sort of validate that. Once you've done both of these processes, you can then apply it to a new data set, okay? So I've got a new data set here. This is an unclassified group of data. It's got a bunch of vegetables in it. You can see I've thrown in just for interesting, I've thrown in a carrot and a red jalapeno. If I was to play with this though and try my train classifier, I'm sick or something. Otherwise I'd be able to do this. I probably can tell what a carrot is, but let's say I can't. I might find, okay, well, there's 6 tomatoes in this mix, 4 jalapenos, 2 onions, and 2 limes, right? But that carrot, it turns out, it's never seen a carrot, right? So if I'm using a supervised learning technique and I'm trying to train it with something that it's never seen before, it's actually going to get it wrong, but it's going to tell you an answer nonetheless, okay? It doesn't say, I don't know what this is. It still says, I think this is a jalapeno because it's long, which is a little weird. If you've tasted carrots and jalapenos, I'm pretty sure you wouldn't mix them up. But if you took a red jalapeno here, for instance, maybe because it's red, it's actually queuing off of it and it thinks, oh, well, that's actually a tomato, okay? And so you can get these misclassifications, but the misclassifications can happen with any type of learning, supervised or unsupervised. But with the supervised learning, it does happen at some rate as well. So these are the types of problems that we can come up with supervised learning. So here's an example of using supervised learning. This is using XMAP tools, which will be somewhat of a competitor for our software. So XMAP tools, they've used supervised learning as the way to do their learning for their program. In order to do it, you have to select a group of pixels and then label them as a particular type of entity. Once you've done all that labeling, you can then classify it, and then you can get something like this based on that map. So this is not just based on this one map, it's actually based on a number of the maps that you're using, okay? So it's based on multidimensional data. And from that, it's been able to classify all of these different parts of the sample based on what you think they are. Now, let's say that you're an untrained user and have a reasonable idea, but maybe not entirely. Maybe you picked the wrong map to do the sort of selection, and you've selected these 2 little groups right here, and you do it, and you might get something like this. All you've identified here is the garnet and everything that's not garnet. But if you were to actually put that too close to the edge, you might get some cells that cause it to classify it as something else. So you can have trouble with this because maybe there's more dimension, maybe there's more groups in here than what you're actually seeing when you output this. So you have to be a little bit careful when you sort of do it like that. Okay, so let's look at the unsupervised learning. That's sort of the approach that we do. Now, I'm going to start with principal component analysis, and principal component analysis is useful both on its own to look at data and try and understand data, but it's also useful for as a way to pre-filter and precondition your supervised learning. So it can be used in both sort of applications. Well, let's say I've got a data set here with X and Y. These just are a bunch of random points that I've put. I've made them somewhat along a line and then added a bunch of noise in X and Y. The first thing, of course, that you would do with a data set like this is probably try and fit a line to it, right? So you fit a line to it, and you're going to get this red line right here. Turns out when you're doing principal component analysis and regression, you're doing the same thing for that first principal component. First principal component is going to be the linear regression of your data set, okay? And then you get a score that goes with that principal component. So that principal component is defined by a vector. That's V1 here. It has a couple of components, and these components basically define the orientation of that line. You can then define a score that goes with that principal component. That's basically how far it is from the mean or in the center of that data set from one side to the other. And what this has done by doing this principal component analysis is you've found the axis of maximum variance of the data. So basically you found the line that spans the largest spread in the data set, okay? But principal component analysis is actually looking to develop a set of basis functions that are orthogonal. So everything's at right angles to each other, but we're going to do this in multidimensional space. In 2 dimensions, though, it's really easy to conceive of because I can take one line here and the other line here. They're clearly at right angles. This is principal component 2. It's defined by this vector here. So your second principal component is always perpendicular to your original, the slope of your first line. And then when you look at that, it's going to pass through this median, or this sort of this central point in the data here, the mean of the data. And again, it's got components here. So this isn't the way we normally look at principal component data. We normally look at it like this. So all we've done is we've taken this data here and we've rotated it so that principal component 1 is along what would be the x-axis and principal component 2 is along what would be the y in our typical system. And our original x and y axes have now rotated into some other orientation. So whenever you do a principal component analysis, you're not actually doing anything special to the data other than rotating it into a way that's favorable to look at. And so by doing that, we just sort of see a nicer spread of the data. We now spread our data equally on one side or the other, and so about that central point there. And then our x and y vector, our x and y axes can be defined then by the horizontal directions in this matrix. Then, of course, we're interested in the scores frequently. We might just look at the scores when we're actually trying to do something with those to maybe make some sort of decision. So that's basically just flattening the data in x, collapsing it all onto the principal component 1 axis, or we flatten it into the principal component y axis. And then by doing that, we basically get these scores here. So let me give you an example that actually will probably make sense to most of you as geoscientists. So what I've done is I've taken a set of plutonic rocks with SiO2 and the full suite of major elements. So I've got 132,000, nearly 800 samples in the data set here. So you can do this with a very large data set then. I take this data set, I run a principal component analysis. In the end, what I can do is I can then, I've taken the average of each of these rock types and then plotted its score on the principal component 1 and principal component 2 axis. And you see something very interesting and something that you would completely expect as a geoscientist, that you have one axis that is basically defined by mafic to felsic rocks, and another axis here, or not a group of data, sorry, not another axis, but sort of a grouping of data that's defined by basically how mantle-like is it, going from mantle peridotite into a volcanic rock pickrite that's sort of a high temperature extract from the mantle. Okay. We can also see how the different, our original data vectors look like. And these can tell us important things. So this SiO2 one almost perfectly aligns with the orientation of these rock types. So that's basically our mafic to felsic rocks. So SiO2 in one direction and iron in the other. And then again, mantle this way, you can see magnesium oxide, of course, is the most important for defining how mantle-like it is. And if you talk to most geochemists, you'll see that that's how they sort of interpret their data to first order. We can also look at how many vectors do we actually need to explain this data set. By doing that, we can see that in terms of our explained variance, we get over 90% of our explained variance in the data, so our variability in the data, by just using 2 vectors. And these 2 vectors here are defined by these principal components there. Okay, so now I'm going to do the same thing, but I'm going to do it with one of those laser maps. So I'm going to take that garnet that we were looking at earlier and all of these different analytes that we have here. After I do the principal component analysis, what I can see is that in terms of the cumulative variance, I only need about 5 vectors here before I define more than 90% of the variance. Okay, so I explained that more than 90% of the variance from those 5 vectors. And then I can look at those scores as a map. And here are the different maps that are created from those scores. And we see some interesting things based on this. The first one, we see a nice core to rim zoning in the garnet. In the second principal component, we see a actually rim to core zoning in the garnet. And the third one, we actually see these fractures and one of these other minerals that's outside of the garnet. In the first principal component score here, we see another one, and then the third one, we can see, again, another one. If we look at what these elements are telling us, so all of these elements here that have a color that's blue or red are telling us how important they are for defining that principal component. And what we find is here, it's mostly the majors that are associated with garnet, and it's the mid to heavy rare earths that you find in garnet in that first principal component. So that's telling us exactly what we see here. In the second one, what we see is we actually see pretty much the same elements are important for this second principal component, but the mid and heavy rare earths are now actually negative instead of positive in terms of the vector components. And so that's telling us about the core to rim zoning and how it's different for the majors versus the versus those trace elements. Okay, so that's principal component analysis. Let's look at cluster analysis, which is another type of supervised learning, but this is actually going to be a little bit more useful for grouping our data and doing some analyses. So the k-means algorithm, which is a pretty simple one to understand, it works like this. You basically take a random set of data. You have no idea what they are. I've got them grouped here because I've actually defined this. I've actually taken 3 groups of points with some center that I know, and then basically created a random cloud from each one of them. But in reality, we wouldn't know what these clouds were related to. We just have clusters in the data and we're trying to find those clusters. Okay. So the way you do it is you randomly assign a set of clusters. After you randomly assign a set of clusters, the next thing to do is assign each point in that cloud to the nearest center. And then you compute the distance from every point to that center. And then you find the average of that new cluster, and that gives you a new center to that cluster. You then do that again and again until that you sort of get a cluster result. The group centers no longer change, and you can do something like this. So here's my random set of data. Again, I have no labels. I have no idea what they are. I'm going to take a few random points there, and those are going to be my cluster centers. Okay. From those cluster centers, I can basically draw a line between each one of them. And then I can draw a perpendicular to the line of each one of those. And those perpendiculars of those lines, those lines intersect. Where all 3 of those lines intersect, it allows me to sort of separate these data into different groups. And that's how I assign them to those centers. Okay. And then I would do this again and again until it settles down. And in the end, I would find my cluster centers are those white stars are actually, no, sorry, the oranges are actually the averages of those clusters. And the white stars are the original centers of the data set that I gave it. So you can see that it did reasonably well. You can see that some of the data, so like the blue on the, let's see, left-hand side, you can see that there's a few of the blue ones on the left-hand side that sort of get scattered in with the others, and it separates them into their groups so that they're mutually exclusive, even though in reality they could be some overlap in the data. So that is one issue that you have to deal with. Supervised learning sometimes can do a little bit better of teasing out some of those where there actually is a little bit of overlap. But this is much faster and much easier to do, and you don't have to be an expert in machine learning in order to do this. So looking at these garnet maps, again, here's just looking at different parts of the garnet. So this is just picking out for the analytes and the different features that we see. And what we want to do is we want to see if we do this fuzzy clustering on the data, do we get these same sort of groups? So fuzzy clustering is like doing that k-means that I showed you just a second ago. The only difference is fuzzy clustering also allows you to say, okay, well, maybe this didn't fall into this group. It actually is in this group. And so it allows for some overlap in the groups, and we'll get a score that's associated with that. This is the result from this. And you can see that the result is reasonably similar to that trained classification that was done earlier on this data set. and we look at the fuzzy cluster scores, this is where it actually gets really interesting, because now we see how confident are we in each of the data points that fall into each one of these clusters. And if you look at, say, the rim or the core or the garnet here, you can see that there's some variation here. It's most certain about the center of it, and then as it goes out a little bit further, it's most certain right here, and it goes out a little bit further, it's a little bit less certain, and it may ascribe that to one of the other. It could ascribe that to one of the other regions just as easily as it puts it into here. And here's the next cluster that sort of overlaps with this one, and you can see. So it's basically saying there's clearly some overlap as you're going from the core of the garnet to the rim, which you would expect from a diffusion sort of profile. But now's where you get to play with the stuff and actually use this for what it's best at. Now that we've been able to classify each of the points in here, we can pull out those data points in the program. And these were actually created in the program, and I just exported them. And what we can do is we can do things like create trace element compatibility diagrams using each of these clusters as a group to define different, or to group the data and then produce that trace element compatibility. And we can see our core to rim profile and see how it varies in these rare earth elements. And we get a little bit of statistics on that too, because of course there's some variation within those data. Here's a ternary diagram, which I've also implemented in there. You can't see all of these because they actually overlap quite a bit here, but the garnet core, rim, and sort of gradient area in the middle all sort of overlap in this area here and all sort of bleed a little bit to here. The core actually doesn't bleed as much, but the rim actually starts to bleed towards this corner here. Now, I don't know if I've actually pulled out sensible elements in order to do this. I'm not a chemist. I just play one on TV. And so, you know, you can probably do something far more magical with this data set than I can. But anyway, this is sort of the idea behind the Laser Map Explorer, is allowing us to sort of explore these complex multidimensional data sets in a quantitative way and hopefully get some sort of statistical information out of them as well. But the new version that Shivin is writing for us is written in Python instead of MATLAB. That has a few advantages. Not everybody in the world has access to MATLAB, especially at companies and things like that. So by writing it in Python, it's actually going to be accessible to more people. It's going to have improved functionality and fewer bugs because I'm not writing it. We're also going to allow for creation of custom maps. So you can look at ratios. Will allow you to do. There's a calculator down here will actually allow you to do things like produce like rubidium over strontium times 5 if you wanted to, or whatever. It's got a larger canvas than our original one does. It allows you to put in multiple maps simultaneously. You'll also be able to mix and match maps between the isotopes, ratios, histograms, whatever you wanted to put next to each other. You'll also be able to process the data in batch. So you'll be able to not just process one map from one sample. You'll be able to process all the maps from all the samples at once. So that can be really handy when you're sort of trying to understand how all of this work. Another thing we'd like to add to this, which would be really interesting, would be doing some diffusion modeling. One dimension shouldn't be terribly difficult. That should be fairly easy to do with this. The software already exists, so we just need to sort of write some of that into ours. But doing two-dimensional would be something that's really interesting and hasn't really been done, I don't think much, even if at all. Two-dimensional diffusion modeling, multi-element diffusion modeling. From that, you can also do things like maybe produce temperature calculations or produce date estimates, things like that, using the ratios and some of the stuff that Darwin's doing. So Jared's been working on a number of codes to do some really nice dating, and we could incorporate those into this, and certain dating techniques might be possible through this sort of software. And like I said, the last thing we might want to do is add additional types of maps other than just LA-ICP maps. So I think that's all I have. So thank you very much.